right, guys, we're onward to section 6.3, and this is where we're going to learn the Pythagorean theorem's converse. That's right. As we've seen the introduction here, of course we've seen it this year, the converses of our theorems aren't always true, but it is going to be true for the converse of the Pythagorean theorem. So we'll pick that one up today. It's not just going to be that, though. We're also going to pick up something neat here that we'll refer to as this, the Pythagorean theorem plus theorems, okay? More things we can deduce about triangles that are really related to the most famous theorem in the history of geometry, the Pythagorean theorem. And we begin now. All right, not too bad of an introduction, I don't think, here. And we're just jumping right into it here. We're getting the converse of the Pythagorean theorem. And that, of course, is a converse here. Just a reminder on converse here is that if you actually think about the Pythagorean theorem, which we had last class, right? We might have started with a diagram that looked kind of just like this, except it had that right angle thing turned in here. Okay, so just quick reminder on the Pythagorean theorem so that you're not the scarecrow, right? A given premise, right? A premise of our situation, right, is that we have to find ourselves with a triangle, right? Triangle ABC, for instance, down here is a right triangle. Right? That's our opening premise, okay? Opening premise here. And then we can apply the Pythagorean theorem by if we know that triangle ABC is a right triangle, then we can deduce what will follow from that is that thing that when you walk up to somebody at a college party, they're going to say this, right? You're going to ask them, hey, what follows from I got a right triangle right here. Tell me about it. They're going to say, well, a squared plus b squared equals z squared. So today we reverse the process, right? There are a lot of ways we can think of reverses of our if-then statements. Are they negations? Are they the reverse negations? No, it's not going to be negation here. So we're not going to talk about things that are not right triangles, at least yet. Later on, we'll talk about things we can prove that triangles can't actually be right. But right now, we're going to prove that triangles have to be right if the converse, the reverse of the situation is going to be true here. So just a reminder how you go from an original implication, right? A proposition like this, an if-then proposition like this, to its converse. So if we have the converse of the Pythagorean theorem, of course, we're going to go the other way. If we have a triangle ABC, so that's still part of our given premise, I guess, but the key criteria of it, right? The actual thing that differentiates it from just any triangle ABC is that I'm going to have with side lengths a squared plus b squared equals c squared. So if I can satisfy that equation, then I will be able to deduce that the triangle ABC is a right triangle. So it just turns out that this actual formula is pretty important, right? It's pretty important. Not only if we have a right triangle, would we know that the sum of the squares of the legs of the right triangle would equal the square of the hypotenuse. If we have any triangle, and we don't know if it's right yet, don't know if it's right or not at all, but we take the two smaller sides. And I say smaller sides because in this diagram here, we don't know if it's right yet. But we have smaller sides. We have smaller side A, we have smaller side B. And if we knew that A squared plus B squared happened to equal C squared, right? The sum of the squares of these two sides equals the square of the remaining side, the third side here, we would know that it would have to be a right triangle. And we're going to do this by proof. We'll actually prove it in a second here. Okay, let's fill in the rest of this, though, because you want to write your theorems down. Yeah, I probably write it like I like putting in my notes those little circles that I put down in my diagrams here. I think that's good. Normally I start geometry by talking about if-then statements and logic at the beginning of the year, and all these are broken down logically as if-then propositions, right? What's my premise? My premise in this situation, the converse of what we proved on Friday's class, is that if we have the square of one side of a triangle is equal to the sum of the squares of the other two sides, right? This is how your book words it out. I'd probably word it a little bit differently. But if the square of one side of a triangle, so just the largest side, right? It had to be the largest side, would have to, the square of this side with the side like C, for instance, would have to equal the sum of the squares of the other two sides, so a squared plus b squared, then that's going to be enough for us to deduce that triangle has to be a right triangle, okay? So that's why I had that little circle earlier here, because this whole thing, our given here, right, our given premise is we got this c squared equals a squared plus b squared, or a squared plus b squared equals c squared. That's normally how in college parties we say it is. It's a squared plus b squared equals c squared. I didn't go to a high school that did. That went c squared equals a squared plus b squared. You must have gone to some crazy private school or something like that. Anyways, that's our premise. What follows from it, of course, right? Triangle ABC is a right triangle. And this is what we're going to prove right now. Okay, so take another second or two if you haven't yet already. put it in your notes, the converse of the Pythagorean theorem. I know it's pretty obvious. It seems pretty intuitive. Like, you know what the Pythagorean theorem is. You can explain the converse. But I trust you, the people who write down more, right? People I see their notes, they're writing down more, generally do a lot more thorough work, right? They get a chance to bond with these words here, and then they second guess themselves. Does it have to be written this way? So when you're writing it down, you're second guessing yourself. You're making sure, you're double checking you understand every part of it, or if you have more questions to ask. That's one of the benefits of actually putting this notes. Okay, so take 5 more seconds, write it out, and then we're going to prove this thing. Let's buckle in, get ready. 5, 4, 3, 2, and 1. All right, let's do it. Let's get it out of the way. Move our given premise, the thing we're trying to prove to. Again, we start with this triangle. It's given to us that a squared plus b squared equals c squared. We don't know it's right yet. So it's just the complete reverse of what the Pythagorean theorem is here. Okay, this is kind of a neat proof. Like, it's just kind of a neat proof just to see go down here. This proof is going to sort of rely upon, I mean, I would never expect you guys to prove this entirely on your own. That's kind of a neat thing about mathematicians and other folks who kind of studied this stuff before, is they've worked with one another and they thought, oh, this is a neat way I can prove it. And nobody can argue it with me about it. So you're going to see in a second. Okay, so what this proof involves is actually building a right triangle, right? This is going to involve building a right triangle with side lengths A and B, for instance. Okay, and what makes a right triangle? I need a what? Okay, so let's just maybe start doing this one in here. Get a statements, reasons. First step in this one here. So we're going to build a right triangle with legs A and B. Okay, and if I have legs A and B and it's a right triangle, I'm going to be able to prove something about C being related to the hypotenuse of the right triangle I want to build. But anyways, first step of this here is getting a right angle here. So we're going to draw a right triangle, EFG, with legs A and B. I'm allowed to do that, right? You're allowed to draw a right triangle in duplicating a couple lengths here. We'll get the reasons down in a second. But first of all, right, obviously I can draw a right angle. I put the right angle symbol in right there because we know, right, from the protractor postulate that any given angle has a measurement between 0 and 180, and it can be 180 if it wants. It can't be 0, but somewhere in between. So if I have an angle that's, 90 degrees, which is a right angle, I'm allowed to draw because I know that 90-degree angles exist. So I would be able to draw a 90-degree angle, okay? Once I've kind of indicated this is where my 90-degree angle is going to be, I can certainly duplicate this leg over here and that leg over there, right? Because those are distances, right? By the ruler postulate says that, well, this segment has a length of A, this segment has a length of B, so I can just tack on, I can make a 90-degree angle with a side, right, a segment coming off. We're ending with, normally an angle is like 2 rays, right, going on forever, but we'll just find that segment length A and this segment length B, and then, right, getting those segments here, that's the ruler postulate, right? We're just copying those lengths, right? Any given segment has a particular length that is a real number, okay? So you can find more segments of that length, of that particular real number. You can use a ruler to rule off the same length here, okay? So 2 reasons down here, but I wanted to build a triangle, so we're actually need a few reasons. So I didn't duplicate an angle here, so we didn't know if this is a right angle or not. I just drew a 90-degree angle. I'm allowed to do that by the protractor postulate because 90-degree angles exist, right? Angles are somewhere between 0 and 180. Need to draw a right angle? Boom, I draw a 90-degree angle. Ruler postulate is going to allow me to draw these side lengths of A and B. But then question, what's the remaining thing that we need to do to draw the triangle? Okay, if I move A over and I move B over, I draw those. How do I finish a triangle? Oh, right. I draw a segment. I connect the endpoints of this segment with length B and the endpoint of this segment with length A, and boom, I got a triangle, right? I've joined 3 non-collinear points in a plane, right? So I fit the definition of a triangle, okay? Last step, what was that last step when I connected the ends of this? Well, this would be a leg, right? This would be a leg of a right triangle. When I drew in the hypotenuse, well, how can I justify that? Well, I'm just connecting that point to that point here. And through 2 points, exactly 1 line can be drawn, okay? And I'm calling that length N right now, okay? In our proof here, a pretty neat proof of this one here, I'm not redrawing triangle ABC again. I'm taking that length and a right angle. I'm allowed to do that by the ruler postulate and the protractor postulate, okay? Because I took the lengths and I took an angle measurement of 90 degrees. And then I connected EF right here. I'm drawing triangle EFG. I connected EF because through 2 points make a line. Here, I don't know that this is equals C yet, okay? Why don't I know that yet? Well, we didn't know if this was a right triangle yet. We don't know if these are congruent yet, right? We simply just copied those 2 with an angle here and connected them, okay? We haven't proven yet that this length of the hypotenuse of this right triangle is the same as the length of AB, right? Which is just a side of this. We don't know if this is a right triangle or not yet, okay? But we can prove it, Okay, we can prove that they're going to have to be the same. Okay, why? Well, check it out here. We know here that because it's given to us that this triangle fits that a squared plus b squared equals c squared formula. Okay, and what we're doing, we're proving the converse of the Pythagorean theorem. We know that's true. What do we know about a squared plus b squared in this one? Right here, we know that a squared plus b squared equals c squared. What do we know about a squared plus b squared in this triangle that we just drew out? Right, well, we know that a squared plus b squared equals n squared, whatever this remaining side is here. Remember, I didn't copy c. I just drew those together based upon the fact that this is side length b, this is side length a. I just connected endpoints, okay? So I don't know that n's the same as c yet, but I know that n squared must also equal a squared plus b squared. How do I know that? Well, I drew what kind of a triangle? I drew a right triangle. So that's the Pythagorean theorem. So here we're using the Pythagorean theorem to get to its converse, right? We drew another triangle, used Pythagorean theorem, a squared plus b squared equals n squared. And so that means n squared is going to have to equal what? Well, what's given to us up top here? We haven't set our givens yet. So c squared equals a squared plus b squared. The opening premise of this is that we have a triangle. And the Pythagorean theorem's formula works. So is it a right triangle? Is the converse true? So I'm getting my given in here. Now looking at this should be jumping out to you at this point in the year, right? What's going on here? What's going on in these two equations? Well, the same thing equals n squared and c squared. C squared and n squared equal the same thing. When two things each equal the same thing, then they equal each other. So that's the transitive property. Save a little space here because your book doesn't show all steps at this point in time. You just pull this from the book. Transitive property n squared equals c squared. So then how do I know c equals n? Well, the book hasn't really given you the reason for that, but you obviously know that in algebra, if you have something on one side of an equation and something on the other side of the equation, you can take the square root of both sides, right? Take the square root of both sides and equality will be preserved, okay? So we'll just call that the square root property of equality. They don't have the square root of property of equality in your textbook, but just call it that, right? Because that's basically what it is, right? If I just have positive values, right? In geometry, that's a nice thing too. So I know that n squared has to be positive. I know c squared has to be positive. Squared has to be positive anyways, but I know their square roots are positive, right? C must equal n. It must be the positive square roots of n squared, and it's c squared. And those are the same, okay? So anyways, c now equals n. So if c equaled n, well, hey, I copied a over here to there. I copied b over to there. So you know what? I built two congruent triangles. Triangle ABC is congruent to triangle EFG. Why? Right? Why are they congruent? Well, SSS congruency. So I did all this work to prove that N is congruent to C, right? I duplicated A and B, right? I did that over there, okay? So what have I now proven about this triangle? Now let's get our attention back to the triangle where our opening premise was from. Triangle ABC had a squared plus b squared equals c squared was true. What were we trying to prove about it? We were trying to prove that this had to be a right triangle. And what can I do now to get that there? I can get this. Angle C needs to be a right triangle. That would be through CPCTC and definition of right triangle. Okay, so CPCTC would tell us, right, that angle G, right, because it's a right angle, I drew a right triangle over here. Angle G has to be congruent to angle C because check it out here. G and C correspond to one another, right? They're in the same positions here in a congruency. So G and C are both congruent. Therefore, right, there's CPCTC, they're both congruent. And G is a right angle, okay? So they both measure 90 degrees, right? And they would have to equal each other, right? So we can deduce here that angle C has got to be a right angle because this is a right angle, and they're congruent to one another. Okay, so then do we get there? Have we gotten to the final step of the proof? No. Well, our goal is to prove that triangle ABC is a right triangle, but here, now we know that triangle ABC, that has a right angle. So why do we know it's a right triangle? Well, just by definition, right? That's what a right triangle is that it is a triangle, right? A triangle that has one right angle. And boom, we've proved that, and now we've gotten to it here. The converse of Pythagorean theorem, certainly a proof that comes up a lot in problems. Is this a right triangle? Is this a right triangle? Here are the side lengths. Is this a right triangle? It's super easy for test makers, right? Whether it be standardized tests, advanced tests, or just me. Remember, I don't write the quiz problems. The quiz problems write themselves. They choose me. So, anyways, it's easy for us to come up with questions on this. So, know the converse of the Pythagorean theorem. If the square of one side of a triangle is equal to the sum of the squares of the other two sides, right? Starting out with that a squared plus b squared equals c squared, then we can deduce it has to be a right triangle. Okay, so the more famous thing is that you have a right triangle. Then you know, right? If you have a right triangle, then you know that a squared plus b squared equals c squared. That's sort of what the Scarecrow tried to say and Homer tried to say, but they butchered it. This is the converse of the Pythagorean theorem. One thing that obviously comes up, I've kind of been hinting at this quite a bit the past few classes with you guys here, is Pythagorean triples, right? Pythagorean triples. So keep an eye out for these. These become more important now than they had been even in the Pythagorean theorem section, okay? Why? Because if you get 3, 4, 5 for your side lengths, what can you say? Well, it's a right triangle because that's a Pythagorean triple. We've seen that pattern much, 3, 4, 5. And even a 3 to 4 to 5 ratio, right, is going to be a right triangle. Okay, because we've seen 6 squared is 36. 8 squared, 64. What's 36 plus 64? Oh, it's 100. Okay, so 6, 8, 10, right? Square root of 100 would be 10. 6, 8, 10 would be a right triangle, right? Would be a right triangle. So we've seen this pattern again and again and again. So it could be kind of nice for you guys to get just pitched one of these random Pythagorean Pythagorean triples and just say, yes, that is a right triangle. And I know it right away. Okay, so it saves you a lot of time and allows you to move through problems more efficiently, right? Because it's saving you time. But more importantly, I'd say it frees up your brain space for the more challenging stuff, because I'd love to get you guys there. Love for you guys to get there, right? Or get yourselves there some way. Okay, so they can save you a lot of time on, the high school, SAT, college, like advanced exams. Geometry problems actually come up in like business school, like entry stuff, the GMAT, right? So they want to see how you can think deductively and connect things. So not to scare you at all, but it's in your best interest, right? You might as well learn it now. We're all here together. Okay, so 3, 4, 5 is the most common one for a Pythagorean triple. Right, it has to form a right triangle because 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, right? And square root of 25 is 5. So the 3, 4, 5 works out. Okay, so in your textbook, they sort of call out this Pythagorean triple thing to you. It might just help just to write them out real quick, right? It might just help just to write them out real quick so that you have some simple ones to look for, simple ones to keep your eye out for, because they'll help you move more quickly, okay? So just to clarify this, right? Any multiples of these work. So 8, 15, 17 works, right? 8 squared plus 15 squared equals 17 squared. Okay, that's going to be a right triangle because that's a Pythagorean triple. Like, because 64 plus 225, that equals what? 289, right? That's 17 squared equals 289. And yeah, it does, right? So 9 there. 4 plus 5 is 9, and 6 plus 2 is 8. Yep, 289 here. Okay, so that is a Pythagorean triple. That would have to be a right triangle. Why? Well, we'd be given, if we're given this, we're given a triangle, right? We don't know if it's right or not here. It doesn't really look right here, but we're given with a side length 8, a side length 15, a side length 17, and it makes the a squared plus b squared plus c squared true. So it satisfies the converse premise, right? That we have a squared plus b squared equals c squared, right? A squared plus b squared does equal the square of this remaining side, this third side here. Therefore, we can deduce has to be a right triangle. Has to be a right triangle. Goes both ways here. Okay. So 8, 15, 17 works. Check it out. 16, 30, 34 works. How do I know that? It's in the same ratio, right? It's in the same ratio here. Here we'd be just like, so here we're squaring 8. Here we're squaring 2 times 8. Here we'd be squaring 2 times 15. Here we'd be squaring 2 times 17. So right, this would just be like 4 times as high, 4 times as high, 4 times as high of the above thing here. So it would still work out, right? You're just multiplying. So it's basically just multiplying this original equation by like 4 to get to this, and then by a 16 or 4, I don't know, a certain amount here to get to the next one, right? 24, what's the next one here? 45, 51, right? There's another Pythagorean theorem triple. So Pythagorean triple. So keep an eye out for these, 7, 24, 25. Just write them out in your notebook really quickly. Keep your eyes for them. You're like, I've seen 7, 24, 25, 4 or 5 times, right? I'm going to remember that. I'm going to be on my lookout for it because you don't want to see the same thing again and again and again. Realize I could just hopefully memorize that one and then just like move through my business a lot easier with some of the target problems. Spend my time on those ones, okay? 5, 12, 13, very, very common. So is 10, 24, 26. So is 15, 36, and what is this here? 39. Sure, works out because it's a multiple of 5, 12, 13 makes a true equation. Okay, 5 squared plus 12 squared equals 13 squared. We've seen this one already. 25 plus 144 equals 169. But if I doubled it, right? So if I do 2 times 5 squared and 2 times 12 squared and 2 times 13 squared, it's gonna work out as well here, okay? Because it's gonna be the same thing. You're basically multiplying this whole equation by 4, right? By 4. And if I multiply the left side by 4, and right side before, right? Because I got the 4 from 2 squared. That's multiplication property of equality. So sort of through the multiplication property of equality, right? That's how you can justify that multiples, right? Multiples of stuff we've seen, we know is true, also has to be true, okay? So 15, 20, 25, that's in a 3 to 4 to 5 ratio. That's sort of our most common, that's our most famous Pythagorean triple. And we can apply that to any multiple of 3, 4, 5. All right, so anyways, let's kind of summarize a little bit here. Yeah, I mean, I kind of talked about this a second ago. I don't really need to do this here. Oh, wait, no, this is actually leading us to a new observation. Okay, so check this out here. So we talked about what? What do we have to talk about today? We had to talk about the converse of the Pythagorean theorem. Now we transition into now we transition into the Pythagorean theorem plus theorems. Okay, so we have 2 more theorems here that's related to Pythagorean theorem, and it's not going to be related to right triangles, right? It's going to involve not right triangles here. So check this one out here. So a triangle with the side lengths 8, 15, 17. It's got to be a right triangle, right? Because as I explained in the last slide here, 17 squared, so c squared would equal a squared plus b squared. These 2 sides here, we square both of them, add them together, equals the square of the remaining side, a third side, the largest side here. So then a question becomes, is there something we can deduce if that side length of 17, so we know that 2 things about the Pythagorean theorem, that a squared plus b squared equals c squared, it could either be true or it could not be true, okay? So let's say we're given a triangle, right? What if we're given a triangle where the hypotenuse, and we put hypotenuse on here, you wouldn't have a hypotenuse in this situation, but what if the largest side is larger than 17? What if it's shorter than 17? Is there anything we can infer about that situation here? Okay, so let's say that this is 8, 15, 17. Okay, 8, 15, 17 right here. What would you know? Well, this would have to be a right triangle. Okay, a right triangle right here. Okay, but what if the remaining, it would have to be a right triangle because this satisfies the a squared plus b squared equals c squared. It satisfies the converse of the Pythagorean theorem. What if this side 17 here were just a little bit longer though, okay? Maybe I'll tilt it upward too. Maybe I shouldn't have, this is really ugly here. Okay, what if it's a little bit longer? Go a little bit, I'll go much longer maybe. I'm gonna go much longer here, okay? What if it's a bit longer here, but I still have, right? I still wanna do this 15 and 8 thing right here. What about that? What can we potentially infer? So I'll take that one 15, and then I'm going to do 8. Well, I'm going to go a little further, 15. And this looks like it's probably about 8. Is there something we can infer about a triangle where this is definitely greater than 17? Okay? It's not a right triangle because it doesn't satisfy the converse of the Pythagorean theorem, right? It doesn't, and I guess we don't know that yet, right? Like what's going to happen if it doesn't satisfy? Could it still be a right triangle? Doesn't look like it to me. So I want to put a little question mark here. It's not a right angle. Is there something else we can infer? What if it's shorter than 17? Okay, what is shorter than 17? I want to go really short. Okay, what I want to go really short here. Boom. Okay, this is definitely way less than 17. And then maybe I'll copy this side length, right? This is 15 equals B, 18 equals A. I want to go a little bit shorter here with this. I went way shorter than the 17, right? There, that's our C in this one, so that's the other side. Okay, I want to go way shorter than that, so it's not even the longest side here. But I'll do this side length of B. It looks like it's about this. I'm just doing a dramatic. Oops, I guess I couldn't have done it that way because then I can't have side length of 8. So maybe we'll do my side length of 8 first. Maybe it looks something like this. Okay, side length of 8 is about this. And then, not quite, okay? But anyways, here's my 15. There's the less than 17 here. What can I say about this? Is that a right triangle? Is this a right triangle up here? What do we know about that angle? Okay, that's sort of what the next things we're going to get at here. And let's just get it in front of you guys here. What can I say about that angle where that third side is greater than 17? What can I say about that angle if the third side that's opposite that angle is less than 17, right? Less than whatever this squared plus this squared is. That's sort of this idea of this third one here. These second and third theorems we have here. The Pythagorean theorem plus corollaries. We got to it. Stay with me. Stay with me. I got too much more battery life here too. So got to get through it pretty quickly. Okay. Here is the theorem. I get it down. I'll pause for a second and write it down. If the square of the longest side of a triangle is greater than the sum of the squares of the other 2 sides, then the triangle is an obtuse triangle. Write it down. Write it down. Think about it. All right, we're talking about the longest side of this here. So maybe that second diagram I showed you in the last slide wasn't super useful. Let's maybe get some more diagrams here. The square of the longest side. So you almost done writing here, this top one at least. The square of the longest side of a triangle is greater than the sum of the squares of the other two sides. Then the triangle is an obtuse triangle. Okay, so that last diagram I showed was not very useful for the second situation because we need to be talking about the longest side. Okay, so maybe let's break this over here. Try to write it down. Maybe circle that greater than, right? Greater, right? So longest side of a triangle is greater than the sum of the squares of the other two sides. Then the triangle is actually an obtuse triangle. Not a right triangle because it doesn't satisfy the converse of the Pythagorean theorem. So that's why we're applying this Pythagorean plus. Put corollary. It's actually a theorem in your textbook. But anyways, let's maybe go to let me go over to this diagram right here where I actually kind of show this out here. C is the largest side in this triangle right here. And we'll start with just looking at the right triangle situation. We have here B. We have here A. What do we know? A squared plus B squared equals C squared. Okay? Equals, so here, maybe I'll put it down here. A squared plus B squared equals C squared. Therefore, okay, it's a right triangle. Okay, we're going to use C for our largest side. So what's the question? What if we made C just a little bit bigger, but we'll leave A and B kind of about the same length here? Okay, so maybe we'll make B a little bit later. So maybe I'll redraw A first. Okay, so A, I'll redraw over here. I'm going to go about 4 tick marks, but I'm going to slide it out a little bit so I can make C a little bit bigger. Okay, so maybe this here, this looks like it's about A. So we're just trying to sketch it out here. This would make C just a tad bit bigger. Look, I have this length C right here. Now C's got to go a little bit further. Okay, got to go a little bit further. And it's just a little bit larger. So I'll make this C plus a certain distance X. Okay, right? This here is length C from here to here, right? So C would be roughly like from here to here. And then this is about X right there, right? That's about X right there. Okay, so I know that's true. So what am I going to know? I'm going to know that A squared plus B squared, okay, it's going to be, and I'm going to get rid of maybe the plus X thing here. Let me make the side length D. This equals C plus X, the original thing here. I would know that because this here, if A squared plus B squared equals C squared, this side length here, the whole long thing here is D, it's larger than C, right? It's larger than C. So I'm going to know that here, this is why they do this, I guess. Here, sorry, this is kind of confusing. I'm going to move it around this statement right here. I'm going to put D. So this here is side length D. Okay, it's larger than C. So that means that D squared would have to be larger. It would have to be greater than the square of the side length A plus the square of side length B, right? Side length B. Okay, why would I know that? I would know that because D equals C plus X, which is larger, right? So I made this side larger. If the third side's larger than what would be the hypotenuse in a right triangle, well, what happened? What's your observation here? What can we say about this angle? If this is larger than a hypotenuse would be, if I did A squared plus B squared, and let's say this is the largest side, and that's larger than what C squared would be in the Pythagorean theorem, and then I would know, right, what? This has to be obtuse. This has to be an obtuse angle, and therefore this is going to have to be an obtuse triangle. Okay, therefore this is an obtuse triangle. Okay, and remember side length D, that's my largest side, and I just extended side length C a little bit here. I had to move the A a little bit to accommodate that, but I'm going to know that has to be true. Okay, theorem, bake it in. Right, I think my logic there is good enough here, right? And we could have written out some more steps, but I don't think we need to. Okay, next up, second theorem here, if you haven't written it down. So I just talked about this, okay? Remember, we're talking about the longest side. You got to be careful about this. When you do problems like this, and we'll look at them in a second, always start by looking at that longest side and see how that compares to the sum of the squares of the other two sides, okay? And we're not talking hypotenuse legs here because remember, they could be right triangles, they could be obtuse triangles, could be acute triangles, but always go to that largest side first, okay? Second part of this here, because we want to prove that a triangle is an acute triangle, and the only way you can prove that a triangle is an acute triangle is you go to that longest side, okay? Doesn't fulfill the Pythagorean theorem, good, but you want that longest side square, okay, that longest side square to be less than the sum of the squares of the other two sides, okay? Then it has to be an acute triangle. Let's maybe take another look at this. another kind of diagram out here on my other sheet of paper. Maybe you can put this in your notes. I would probably put this in your notes here, like here, so you actually have something visual to kind of connect with this here too. If I have said side length B, again, this was side length B. I copied it over here. I copied it over here. Now let's do this third scenario, okay? So I still want this remaining side. I'll make it side length E, okay? We'll make this side length E. I want it shorter than C because I want this to, I want to make the statement here, I want to make the statement here be true. I want this to be E squared is less than the sum of the squares of the other two sides of the triangle. Again, not legs, they're just other two sides because this is going to end up being an acute triangle. Okay, the way that I get side length E to be less than C right here is, well, first of all, I got to move this side length A. I got to move it a little bit closer, right? Closer here, 1, 2, 3, so a little bit short of that. So I think we went 4 tick marks down there. So about this. This looks like it's about side length A. Okay, and what do we notice about this, right? This is certainly, the remaining side here is still the longest. Look, that's definitely longer than that, right? That's still the longest side. So my eyes go to the longest side here. We're going to call this side length E. And what does that equal? Okay, well, it equals side length C, and I trimmed down a little bit here. Okay, so look, I tried to do this so that these looked about the same. These, ideally, if I were constructing this, I would do it so I would know that they're exactly the same, or at least as good as my construction tools could do. Here, this isn't equal C. This is shorter than C. Okay, so this is C minus, right, minus y, minus some sort of constant or whatever, okay? So I would know that if this length here were C minus y and I squared that, that would be a lower value than C squared, okay? So if I square E, right, square E, that's less than C squared. So it's going to be less than A squared plus B squared. And what type of a triangle is this? And I'm actually going to circle all 3 of the angles, okay? All 3 of the angles because I know that E is my largest side, okay? If E is my largest side, what do I know about the angle opposite the largest side, okay? This is going to be the largest angle in the triangle. Okay, largest angle in the triangle. The obtuse one was obvious here, right? This is the longest side. Hypotenuse is the longest side here. Right, so the right angle is the longest angle. The obtuse angle is the largest angle here. It's opposite the largest side, so it's pretty easy for us to deduce here. But here, this is still going to be the largest angle in this triangle because it's opposite the largest side. So that's why your brain should always go to the largest sides on this problem here, because the largest side of a triangle is going to indicate where the largest angle is here. And in this one here, because E squared is less than or equal to A squared plus B squared, I know that because it's not this, right? This is when C is big enough so that it actually equals A squared plus B squared, right? We started the Pythagorean theorem here. Because I know this, therefore, this is going to be an acute triangle, right? An acute triangle. How do I know that? This is the largest angle in the triangle right here. And I proved it can't be right. It can't be obtuse, right? Because I have the side shorter than that one here. So this is an acute angle. And it's the largest angle in a triangle. That means that this is also acute. And this is also acute, okay? Because this is less than 90 degrees here, right? Because the side's not big enough for that. It needs at least to be C in terms of how A squared plus B squared equals C squared relates. So smallest angle in a triangle, it's less than 90 degrees. That means both of these are even smaller than that. So also less than 90 degrees. So this is an acute triangle, okay? So here are your 3 takeaways. Here are the things to look at here, okay? Is that if you have, okay, largest side, the square of the largest side is larger than the sum of the squares of the other 2 sides, that triangle is obtuse. The square of the largest side of the triangle is less than the sum of the squares of the other 2 sides, that triangle's got to be an acute triangle. Okay, what if the largest side is, the square of it is equal to the sum of the squares of the other 2 sides? Well, then it's a right triangle. It satisfies the converse of the Pythagorean theorem. So make sure you have these down in your notes, and we'll practice these. Might as well do it right now. Hey guys, we got a lesson right here, okay? Know how to deduce if it's obtuse. Know how to deduce when it's acute. What side do you look at? What one jumps out to you right away when you do problems like this? Look to the largest side. Look to the largest side. And that's what we're going to do now. We're going to practice these. This will be on your exit ticket too. Yes, this is great. Not too bad, okay? So, hey, I'm starting this problem. Guys, I'm going to circle all my largest sides. They made this convenient for us. They set this up here. They made it too easy, I think. Your brain should go to the largest side. Why? Because the square of the largest side of the triangle, that's how it's going to relate to the square of the smallest sides to determine whether it's right, obtuse, or acute, okay? Square of the largest side is larger than the sum of the squares of its 2 smaller sides, obtuse. Smaller than that, acute. Equal to it, Right triangle. That's it. That's it. We got this. Let's got this. Let's jam away on this here. All right, so I'm going to set it up here. Largest side, question mark, sum of the squares of the other two sides here. What do we got here? What do we got here? Okay, number one, let's see. If a triangle is formed with the sides having the lengths named, is it acute, right, or obtuse? So we can deduce that about the entire triangle here. If a triangle can't be formed, say not possible. Ooh, they might have tricked us if we're going too quickly on this. Let's look at this one here. So hold on, maybe I'll try out the Pythagorean theorem, the corollary. It's a corollary. It's a Pythagorean plus theorem here first. 6 squared is 36, and 4 squared is 16. 1 squared is 1, so that's 17. Okay. But what I noticed about this is a lot different. So obviously this is, oops, didn't mean to do that. 36 is larger than 17. So I think maybe, is this obtuse? That's what I think. Is this obtuse? And then I noticed here, wait a second, there's this whole idea of things not being possible. Let's look at these numbers again here. That's actually a big difference here. This third side would be, this supposed third side would be much larger than the sum of the squares of the other two sides. So if you end up with this, you got to ask yourselves this question: is this actually possible to draw a diagram, to draw a triangle with these side lengths here? Who says yes? Who says no? Yeah, sure. Well, you say no. Who says no? Why do you say no? Well, you got to remember here that we have some other theorems that might conflict with this particular situation here. And the one that I'm thinking about here is the triangle inequality theorem. Okay, so remember the triangle inequality theorem. So you have to, and these problems, you got to test two things out. Test it out in the Pythagorean theorem, right, to see the sum of the squares of the two smaller sides, how it compares to the square of the largest side here. But then you also got to remember, are side lengths like this even possible to arrange a triangle? And this one here, the answer is no, because if you add, remember, you have this thing that says the triangle inequality theorem says that any two sides of a triangle, the sum of the lengths of any two sides of a triangle must be greater than the length of the third side, okay? So if we have this one here, we need to know that 6 needs to be, 1 plus 4 needs to be greater than 6, right? Needs to be greater than 6. Is that true? No, that's not true. 5 is not greater than 6, not greater than 6, okay? So just a quick reminder on this one here, this one is not possible, okay? And we can sketch it out to verify it's not possible very easily here. Let's start with this side length of 6 here, shall we? Shall we? Yeah, I think we shall. If we start with a side length of 6, let's do this on top, okay? So let's say that this is a side length of 6. How would I ever create a triangle with a side length of 1 and side length of 4? Because if I go here like 1, let's chop it up. 1, 2, this is awful. 3, 4, 5, and 6, okay? If I go side length of 1 right here, okay, and then a side length of 4, 1, 2, 3, 4, look at that. I can't close up the triangle, right? A triangle is when you connect 3 noncollinear points here. I would need, right, this here. If a side length of 1 is right here, side length of 4 is right here, we're not even coming close to closing that triangle right here, closing that triangle here, okay? So remember, in order to create a triangle, it just needs to be a little bit bigger than 6. So this would be like 2, 2.1, and 4 would work, right? Because that's would be greater than 6. But 1 and 4 don't work here, okay? I'm getting a little bit messy. I might do a different color for each one of these here so that you guys see it a little bit more clearly. So let's try out some other ones here. So maybe we can try the triangle inequality first to see if this one works out here, okay? So is 4 plus 6 greater than 8? Yes, it is, okay? So we know a triangle is possible. Now we need to try it in the Pythagorean theorem and their related Pythagorean theorem plus formulas here, okay? So let's do it here. Largest side, my brain goes to the largest side. How does it compare to the squares, sum of the squares of the lengths of the other two sides here? Okay, so I'm going to compare it this way. 8 squared is 64. Okay, how does that compare to 4 squared plus 6 squared? Well, this is 16 plus 36. And here we end up in a similar situation as we had over here, which is that 64. So the square of the largest side is greater than the sum of the squares of the other two sides here. Because this is 16 plus 36, that's 52. So what do we know? Okay, so our largest side, the square of the largest side is larger than the sum of the squares of the other two sides. So that means that largest side is freaking big, right? It is freaking big. So that means that opposite angle, pretty big as well here too. So we can deduce that this has to be an obtuse triangle, okay? And we get that from the Pythagorean theorem plus theorems, one of those two that you guys just looked at a second ago. Let's keep going, guys. Let's keep going. Do this next one in red. Let's try triangle inequality first so we don't get tricked on this. And we'll get 6 plus 8. Is that greater than 10? And it is. 14 plus 14 is greater than 10, so we know building a triangle is possible. It satisfies triangle inequality theorem. Okay, next up, Pythagorean theorem. Go to the largest side, 10. 10 squared, how does it compare to 6 squared plus 8 squared? Okay, and we know that 6, 8, 10 is actually a Pythagorean triple. So we know that this is 100 would equal, this is 36, this is 64. Okay, so it works out. So it's a Pythagorean triple, so we know it's a right triangle, okay? Because the sum of the squares of the two smaller sides equals the square of the largest side. So we know that a squared plus b squared equals c squared, right triangle. Converse of the Pythagorean theorem works out in that one here. Going to cyan here, high cyan. So we're going to do triangle inequality theorem to see if even building a triangle is possible in this one here. And it is, right? 8 plus 10 is definitely greater than 12. Okay, 20 is greater than 12, so we know building a triangle is possible, right? Given those three sides. Now we try it in the Pythagorean theorem goodness here. Go to the largest side. How does it compare to the sum of the squares of the two smaller sides here? So 144 is 12 squared. 10 squared would be 100. 8 squared is 64. Okay, so here we have 144, and it's less than the sum of the squares of the other two sides here, right? 100 plus 64 is 164. So we know that that third side isn't super huge compared to the other two sides here. So that angle isn't going to be super huge either. So we can deduce that it's got to be an acute triangle. Got some square roots here. Going to black pen now. Triangle inequality theorem. Is this triangle even possible here? Okay, so let's check it out here. Is root 7 plus root 7, is that greater than root 14? Got to go to a calculator on that one. I would go to a calculator. That's your quickest bet to figure that one out if it's actually possible. So root 7 is about 2.645. So I'm going to multiply that by 2 because I got 2 root 7s here. So as long as root 14 is less than less than 5.29, then and it will be, right? Because 25, for instance, would be 5, so that'd be less than that. So so this is going to work out here. As long as root 14 is smaller than 5.3 or so, then we know we can make a triangle of this. And it's going to be, right? Because square root of 25, for instance, is less than 5.3. But square root of 14 is even smaller than that, so about 3.74. Okay, so triangle is possible. Triangle inequality theorem worked out. So now let's just see how the largest side compares to the sum of the squares of the two smaller sides. Okay, so I'm going to do root 14 squared up. Okay, question mark, because again, we want to see how it relates, right? These are just called relation symbols, right? Math is just relationships, right? Seeing how things relate to one another here. So then I'm going to do the sum of the squares of the lengths of those. This should be 7 here, of the two other sides, the two smaller sides here. Okay, see how it compares. And then I get this, 14 squared, perfect, is 14. And that's going to equal, right, root 7 is 7. Sorry, root 7 squared is just 7, right? Does the rooting, is what the squaring does. And then squaring, so I'm going to do this rooting, and I got 7 plus 7. So we're going to know that this is equality here. So we're going to know that this is a right triangle, right? Everything connects together, right? I'm trying to form those connections, right? Everything follows from it. Okay, you with me? You following me? You ask any questions? Feel free to send me any questions if you have them. I normally get questions during this lesson. I quite enjoy that. All right, last one here in magenta. Is this triangle possible? Well, maybe let's just do this quickly on a calculator because we have the root 3 action right here. So let's see here. We got root 3. So we'll do this. So we don't see a number here. That means square root, okay? So that's 1.73. I'm going to multiply by 4. Okay, that's already 6.9. If I add 4 to that, that's larger than the largest side. So we'd be able to connect a triangle with a side length of 8. If our other two sides add up to 11, right, that's greater than 8. It follows, it satisfies the triangle inequality theorem. So we can make a triangle out of it. The question is, right triangle? I don't know. Is it acute? Is it obtuse? Well, I know the answer. Right? I know the answer because I know the pattern. Special right triangles come to us next section, section 8.4. So let's just check it out here in the Pythagorean theorem, right? I circled your largest side. How does your square of the largest side compare to the sum of the squares of the two smaller sides, right? And that's going to determine what type of a triangle it is. Is it acute? Is it obtuse? Is it right? And let's get this thing done here. 4 root 3. You got to square the whole thing. Squaring the length of the whole side here. Okay, so we're going to get this. 8 squared, 64. Okay, 4 squared is 16. 4 root 3 squared, well, 4 squared is 16. Root 3 squared is 3, so 16 times 3 is 48. And we get this. And how does 16 plus 48 compare to 64? Well, 16 plus 48, we can write that as 64. Okay, so 64 equals 64. That means that this is going to, because of this here, it's going to be a right triangle. And that concludes it. Okay, so expect if you didn't watch this video, my TAs to kick this back to you, be like, hey, watch this, you can get this. Just not too bad going through some examples of Mr. Fortin here, because this will be on your exit ticket, a few other problems on your exit ticket. Thank you guys for watching today's lesson. I enjoy doing these problems. Hopefully you enjoy doing them too. If not, just keep trying to figure it out and keep learning. That's what it's all about this year, okay? Asynchronous problem set will be on Thursday. I don't know if there'll be these exact problems, but why don't you just show you this is normally what I do, right? And normally here we'll do this, we'll talk through it, we'll get notes written out. Hey, we take care of our business in class, go home, just try out this problem set. Very low stress. Just be doing problems. Don't put too much pressure on yourselves. Just try to keep up, right? That's what I ask from you guys here, and you ask for help if you really just, I don't know what to do. We'll try to help you here. Have a great evening, guys. I will see you on Friday. And of course, message me about anything. Bye.